In this video, we're going to look at the remarkable Bohr model of the atom, which was able to predict the line spectra of hydrogen. And this was a very impressive accomplishment, as we'll see in detail in this video. So before the Bohr model of the atom, we had J.J. Thomson, who discovered the electron, the first discovery of a subatomic particle. His model of the atom was that it was this large positive charge with electrons, negatively charged electrons, embedded within that large positive charge. However, Rutherford put forward a better model in order to explain scattering experiments. And you may have come across the Rutherford model, which was as a result of alpha particle scattering from gold foil. And the conclusion was, in order to have that scattering occurring, a better model for the atom was to say that that positive charge was actually incredibly localized in a very dense, tiny nucleus of the atom. And then we have all this free space here, and then an electron or multiple electrons in orbit around the nucleus, the proton. However, classical physics would say that if that model is the case, if the Rutherford model is the case, then this electron orbiting the single nucleus here, the proton for the case of the hydrogen atom, then the electron should be continuously emitting radiation as it loses energy and then ultimately collapses as it's attracted towards the positively charged nucleus. Of course, that's not observed experimentally. Atoms are stable, but that's a big problem then for the Rutherford model of the atom. So let's think then, what is it that we do see coming from atoms? If we don't see this continuous spectrum coming from isolated atoms, what is it that we do see? So one example then would be atomic oxygen in the atmosphere of the Earth. This is the aurora borealis, and effectively we have ionized particles from the sun, which cause ionization of molecules and atoms in the atmosphere of the Earth. And what we see with this green light is a very distinct single wavelength of light given off by atomic oxygen as it de-excites. And in fact, we can put many gases within these gas discharge tubes, and we observe there are very particular wavelengths of light given off from various atoms. And in fact, each atom has its own signature of line spectra of photons that are emitted. So focusing in on the example of hydrogen, we observe, there's hydrogen on the left there, we observe all of these various series of spectra, in other words, very discrete wavelengths of light that are given off by atomic hydrogen. Now, Rydberg had put forward a formula that unified these various series of spectra that are given off from hydrogen atoms. And this was his formula, basically had this Rydberg constant, and he would say that the wavelength, 1 over the wavelength, is equal to this expression on the right-hand side, where we just put in integer values of m and n, where n would be a larger integer than m in order for this to be a positive value. But the point is, because m and n are integers, the wavelengths will not be able to take on continuous values, but rather they'll take on these discrete values as shown in these various series, which correspond to particular choices of m and n. Now, let's take this a bit further to see what's going on with the Bohr model of the atom, which is what we're going to be looking at closely in this video. We know that the energy of a photon is equal to Planck's constant times the frequency of the photon, which in turn means the energy of a photon is Planck's constant times the speed of light divided by the wavelength of that photon. So we can rearrange that to say E over hc is equal to 1 over lambda, which allows us to substitute into that expression for the Rydberg formula and to see immediately that if there are discrete wavelengths, there must also be discrete energies. Stands to reason, since energy is related to frequency and therefore also related to the wavelength. So therefore, looking at the Rydberg formula and E equals hf, we can see that the hydrogen atom looks like it has discrete energy levels, given again that m and n are integers, which means those energies cannot be arbitrary values, but they're going to have very distinct spacings as shown in the hydrogen spectrum. So discrete frequencies meaning discrete energies, thanks to E equals hf. So Bohr put forward the following postulate, that electrons in orbit around the nucleus from the Rutherford model are in fact in quantized orbits. And what we mean by quantized orbits is that they have very definite energy states, which are dictated by a quantum number, n, which is an integer value, not a continuous real value, but an integer from 1 onwards up to infinity, 1, 2, 3, 4, and so on. And so his postulate was that when one of these electrons is in orbit, it is in a fixed energy state and it will not emit radiation. But an electron can move between different quantized orbits in these kinds of quantum jumps, these instantaneous transitions between energy states. That he said that the electrons can jump between those states and they will either emit or absorb radiation corresponding to the energy difference between those two energy levels. So we'll look at that in more detail in a moment. Just to note that Niels Bohr did obtain a Nobel Prize many years later after this model, indeed for his work on investigating the structure of atoms, and indeed on his work on looking at the radiation and explaining the radiation emanating from atoms. So that's what we're going to be looking at in detail here. So here then is an electron in orbit around a proton, a nucleus of the hydrogen atom. And what we mean by quantized orbits is that we have very distinct radii as shown in this figure here. So we can't take on any arbitrary radius of orbit, but only these discrete increments in the orbit radius of the electron. Furthermore, we're saying that the electron has an energy state in any one of those orbits, and that it can jump, as shown there, between different quantized orbits. So when it goes up, that would be absorbing a photon, and when it goes down, that would be giving off a photon. So we're going to see again in detail what we mean by this. First of all then, energy levels are governed by these integer principal quantum numbers, n equals 1, 2, and 3, and so on up to infinity. Here then, if we have an electron in this excited state of energy state n equals 3, it can lose energy by dropping down to n equals 2 by emitting a packet of energy corresponding to a photon, which matches the energy difference between the n equals 3 state and the n equals 2 energy level. So we look at the difference and that gives us the energy of the emitted photon, which of course corresponds to one of those lines in the hydrogen spectrum. Okay, and what we'll be seeing in this video is just how perfectly he was able to describe those exact hydrogen spectra by this very model. Next, the example of absorption, whereby if there's a photon of just the right frequency or wavelength corresponding to the difference in energy between two of those energy levels, then the electron, when absorbing that photon of just the right energy, can go up an energy level, or indeed multiple energy levels on absorption of just the right frequency of light. Okay, so that's the core model there. Basically, the energy difference between two integer quantum states, quantum energy levels, quantum number n, quantum number m, the difference between those two states in energy can be expressed in the form of a photon, either emitted in order to drop down an energy level, or absorbing a photon of energy hf in order to go up an energy level. And this all came down to the following key postulate from Bohr, was when he postulated that angular momentum is quantized. So that's going to be the key to his ability to predict hydrogen spectra. So to look into that, let's consider an orbiting electron around a proton here. We know that momentum is defined as the mass times velocity of an object. Here's the mass of the electron, there's its velocity. Angular momentum is the same, or rather it's very similar. It's mass times velocity now multiplied up by the radius of circular motion. And classically, angular momentum could take on any value whatsoever. In other words, there could be any value for the radius, any value for the velocity, and you'd be able to therefore have any value for the angular momentum. Now, Bohr said that angular momentum is quantized. In other words, that product of mass times velocity times radius of the circular motion can only equal an integer multiple of packets of size h over 2 pi. In other words, you can't have h over 4 pi, you can only have a certain whole number n, integer number n, multiple of h over 2 pi. It gives you this quantized set of discrete values for angular momentum. So, key point there then, that n is an integer, 1, 2, 3, 4, up to infinity. No halfway points between those integers permitted. You can't have 1.5, 1.6, whatever it might be. So therefore, given that MVR is quantized by integer multiples of that packet size, therefore we can use a subscript n to denote the velocity is quantized and the radius is quantized, because we're assuming that the mass of the electron, m, is fixed. Okay, so let's now look more closely at the model. Here's the positively charged nucleus of the atom. There's the orbiting electron, and we know that the Coulomb force of attraction between the electron and the proton is simply going to be E, the charge of the electron, multiplied by the charge of the proton, so E squared. That's going to give us the magnitude of the force of attraction between them. So it's the product of the charges divided by 4 pi epsilon naught, in other words, permittivity of free space, multiplied by the radius squared. That's the Coulomb force of attraction. Then we also know by circular motion that the force towards the center of this circular motion, the force towards the center, must be mass times acceleration, and the acceleration in circular motion is v squared over r. So therefore, force towards the center, the centripetal, the center-seeking force, is mv squared over r. Then, of course, we have the fact, again, the postulate from Bohr, and we'll see in another video where that comes from. It's related to what Louis de Broglie put forward in terms of electrons being understood as waves, but for the moment, we'll just accept the postulate as is, that MVR is just composed of packets of size h over 2 pi. So therefore, using these expressions, we can express Rn and Vn in forms that allow us to understand how they relate to various choices of n. Okay, so here we are then equating the centripetal force to the Coulomb force of attraction, and we've kept the quantization of angular momentum on the screen as a reference. Then what we're saying is, to work with these formulae, we can multiply both sides by Rn squared to remove it from the denominator there. And then we can see what we'll do next is we're going to multiply top and bottom here by m over m, multiply the whole thing by 1. The reason for that is that we can now spot an m squared, then vn squared, rn squared, which relates nicely to our quantization expression. So we can write the square of that and substitute it in to the numerator on the left-hand side. So if we do that, we get this expression here. We can then work further with that to rearrange so as to solve for Rn. So Rn, just by rearranging that expression, is clearly given by the expression in the middle of the slide there. And again, if we rework things there, if we do cancellations, we can rework that to get Rn is equal to epsilon naught, permittivity of free space, multiplied by the integer n squared, where n goes from 1, 2, 3 up to infinity, multiplied by Planck's constant squared, divided by pi, mass of the electron, charge of the electron, squared. And this gives us the discrete permitted radii of our quantized electron orbit. Again, n cannot take on values that are not integers, and therefore we cannot have continuous values of r, only discrete values of r. Okay, so let's continue with our model. We could do a very similar calculation as to what I've just shown you to use those equations, centripetal force, Coulomb force, quantization of angular momentum, and then we've solved for r. We could also then solve very straightforwardly for the velocity as well. So we get discrete values of velocity, discrete values of the radius. Now, already we can get useful results from here by choosing the closest possible orbit of the electron, in other words, the shortest radius, by choosing n equals 1. If we plug n equals 1 there, we get what's called the Bohr radius, labelled as A0, just simply given by that expression by setting n squared equal to 1 there. And if we do the calculation there, we'll find that it comes out to be roughly 0.5 times 10 to the minus 10 meters, about half an angstrom. And that Bohr radius happens to be the most probable distance of finding the electron relative to the nucleus of a hydrogen atom. So this visualizes that distance to give you an idea of the sheer scale of space between the nucleus and the orbiting electron. So here, there's the United Kingdom. You can just about make out part of it on the right-hand side there. And that nucleus is actually here represented in size by this Gherkin tower in the center of London. So if we imagine the nucleus, the proton being the size of that Gherkin tower located in London, then the most probable location of where we would find the electron, the orbiting electron around that proton, would be quite incredibly roughly the east coast of the USA. So just consider how much free space there is between the proton and the orbiting electron. So again, this is just an analogy to understand the scale of space between the proton and the orbiting electron. Okay, now finally let's move on to getting the energy of these orbiting electrons. Now the total energy for the atom in state n is given by the kinetic energy of this electron plus the potential energy of the electron. So we know kinetic energy is half mv squared. Now we've already got an expression for the velocity on the earlier slide, which can be found from those equations that I wrote down. And there's Vn there. If we substitute that in, we get this expression for the kinetic energy. Also, we can look at the potential energy. That's related to the charge of the electron, the charge of the proton, and therefore we get minus E times E divided by 4 pi epsilon naught Rn, where Rn is the discrete radius, permitted radius. If we plug the values in for the radius, as we have found before, then we get this expression on the right-hand side. And then we can find the total energy for energy level n of the atom, or in particular, really, of the electron. So there's the total energy, and we can see very easily that these terms on the right-hand side are identical. Therefore, it's plus 1/8 minus 1/4, which therefore gives us minus 1/8 of that term there as the energy of energy state n, where again n is the integer n squared in the denominator there. And so as a quick note, total energy is negative because by definition, when we go out to an infinite radius where n squared, n tends to infinity, then the energy for the liberated electron is taken to be 0. Okay, so let's look at the remarkable result that arises from the Bohr model of the atom. Here then is that expression for the total energy, and there, remember, is the Rydberg formula allowing the expression, just an empirical expression for the hydrogen spectrum. And you remember from earlier on where we said energy is equal to hf, hc over lambda. That allowed us to rewrite this as discrete energy states, in other words, just differences in energies. Now, if we look at the Bohr model, which talks about the energy of an electron for energy level n, we could look at the difference in energy levels of the hydrogen atom by looking at differences between integer values n. So we could use an integer n and an integer m for a different choice of energy states. So let's look at the difference between two such energy levels. We just take this and then we factor out 1 over the integer squared, where we've got an integer level m for this one here and an integer level n for that one there. And to have a positive energy difference, that would need that n be larger than m. And so we can compare this expression. This is the total energy, for example, of an emitted photon when there's a transition between those two energy levels. We can compare that total energy to this expression for the energy permitted of a photon according to any particular choice of m and n. and we'll notice there I'm just highlighting where those integer squares came from just the energy expression as a function of quantum number n, where we've chosen different values of the integer. Then by comparing those expressions, which is what I'm going to do on this slide, there's the Rydberg formula, rewritten in terms of energy. Here is our Bohr model energy level difference expression. We can see immediately that we can compare the coefficients for those two parentheses, those brackets with the differences, the difference in two fractions. So we can compare those two to compare these two independent models. This was the experimental empirical formula, and this is the model from the Bohr model of the atom. Okay, so we've got theory on the bottom, experiment on the top. And experimentally, there was found to be, of course, a particular value for R, which describes the hydrogen spectrum, for example. Whereas this is purely by that circular motion with the Coulomb force and centripetal force and quantization of angular momentum. That's how we've got that theoretical expression on the bottom. Now let's see what happens if we put these together. So if we claim that this should equal that, if this model is valid, then we'd expect HCr to equal what we've got from our Bohr model of the atom. So what happens when we calculate the value of R based on our model? This is the result from our model. What happens if we do that? This is the expected value for the Rydberg constant, and very, very remarkably, the model value from the Bohr model of the atom matches the experimentally found value to within 0.1%. So that's a remarkable result for the Bohr model of the atom. And so therefore, using just this very simple model that we've looked through in this video, we're able to very accurately predict the spectra of light, the very definite photon energies that are given off from atomic hydrogen. And indeed, the model can also work for other simple atoms as well. And so this slide just goes into the various series of different light that is observed from hydrogen, and indeed, just to confirm that those wavelengths, those energies are beautifully found also by the Bohr model of the atom, explaining the energy levels in terms of these fundamental physical constants: Planck's constant, the charge of an electron, mass of an electron, and the permittivity of free space. Furthermore, experimentally, it is known how much energy needs to be put in, for example, to ionize a hydrogen atom, in other words, to liberate the electron. That's the difference between n equals infinity, the difference between the infinite radius, in other words, n going up to infinity, where the radius is extremely far off to the point that the electron is no longer really in orbit around the proton. That energy level by definition is zero, and so we can check that first of all. If we substitute n equal to infinity in here, then of course we're going to get zero. Then we can subtract off the energy for state n equals 1, so we plug in n squared equal to 1 there, and we end up with a simplified version of that expression as shown here. If you convert it into electron volts, then remarkably the 13.6 eV is also incredibly close to the experimentally observed value for what is the energy of photon you need to put in to ionize a hydrogen atom. That agrees to within less than 0.1% discrepancy. Remarkable result, really justifying this Bohr model of the atom, at least for the case of the hydrogen atom. So there we go then, an amazing outcome for the Bohr model of the atom, just by using very basic equations of motion with quantization of angular momentum. We see the ability to predict these rather unusual looking spectra from the hydrogen atom. So a wonderful success for the Bohr model of the atom. The other question now is going to be, why on earth is angular momentum quantized? How do we explain that? And that's where we'll be looking ahead to Louis de Broglie and his postulate that electrons also behave as waves. Thanks for listening.